The SN2 reaction, or nucleophilic, another nucleophilic substitution reaction. This, of course, differs from the SN1 reaction, in the fact that the rate determining step is bimolecular, or second order. An SN2 reaction occurs in a single step. We have some sort of alkyl group with a good leaving group, and a nucleophile attacks from the opposite side of the leaving group, and in a single step displaces the leaving group to give us our product. Now, this results in an inversion in stereochemistry. So if your starting material, such as the one I'm drawing here, is chiral, then when you add in a nucleophile, that nucleophile has to attack from the opposite face of where the leaving group is. The reason for this is what's necessary in order to achieve optimal overlap of the HOMO of the nucleophile with the LUMO of the electrophile. The result here is the nucleophile is then on the opposite side of where the leaving group is, and we get an inversion in stereochemistry. Now, there's a number of factors that can affect an SN2 reaction. We can talk about the solvent and the sterics, as well as the leaving group and the nucleophile. For the leaving group and the nucleophile, it's fairly straightforward. The better they are, so a better leaving group or a better nucleophile, leads to a better SN2 reaction. Now, with sterics, more sterics or more steric hindrance will almost always cause a hindrance to an SN2 reaction. That's because the nucleophile is attempting to attack a fully substituted tetrahedral carbon. And so the more substituents you have around that electrophilic carbon, and the bigger those substituents are, the more they can block that nucleophile from getting in there. So in general, SN2 reactions work great for primary leaving groups. They work sometimes for secondary leaving groups, and almost never for tertiary leaving groups. Finally, for the solvent, SN2 reactions typically require polar aprotic solvents. And that's because if you use a protic solvent can actually coordinate to the nucleophile. And because the nucleophile is involved in the rate determining step, that makes the nucleophile less reactive. And by making it less reactive, we slow the reaction down. So typically for an SN2 reaction, we use solvents such as acetone, or THF, or acetonitrile. All highly polar solvents, but solvents with no acidic protons to provide. All right, we'll end this video by looking at a brief application. And this is one such application. It looks a little different from a lot of other SN2 reactions because of some of the groups involved. But here, if we have S-adenosyl methionine. With this sulfur being positively charged, the lone pair of nitrogen can actually come in and pick off this methyl group. And then we kick out as a leaving group the neutral sulfur, and that's actually a pretty decent leaving group. As a result, we make this molecule here that's used in the synthesis in phospholipids for cell membranes.